Hello, my name is Corey Lee, Sales Specialist in the Southeast Region, U.S. I'll be your moderator today. I want to thank you all for joining us for our PerkinElmer Hyphenation Techniques webinar today. Hyphenation techniques are something that PerkinElmer has done well for many years, and we want to share with you this overview of some of the different configurations we provide. In lieu of our normal in-person workshops, like those workshops, we hope that you have an opportunity to learn something new today that you might be able to utilize in your lab right away tomorrow. I'm going to introduce our speaker today. Dr. Warren Edmonds is the Materials Characterization Field Application Scientist for the Southeast U.S. for PerkinElmer. He specializes in application support for FTIR, UV-Vis, and thermal analysis. Warren received his PhD in Biological and Agricultural Engineering from North Carolina State University. Prior to working with PerkinElmer, he held a research position as a postdoc at the University of Tennessee. More specifically, his experience involves developing chemometric infrared models for measuring biomass, quality parameters, as well as measuring chemical and mechanical properties of natural materials. Warren is excited to share some recent advances in hyphenated technologies. As questions pop up, please type them into the GoToMeeting question text field, and we will be happy to address them after the presentation. I'm going to turn things over at this point to Warren.
Okay, thank you, Corey, for the introduction. And I would like to thank the audience for taking the time to join our webinar today. So I'm going to go ahead and jump straight into the presentation. Okay, so first let's review some of the basics. What is hyphenation in the context of analytical instrumentation and analytical analysis? So simply put, this is coupling two or more analytical techniques. Traditionally, GCMS, this is gas chromatography, mass spectrometry, was considered a hyphenated technique. Now these two techniques are essentially considered a single instrument or a single technique. This is because the sample gas transfer from the GC to the mass spec is seamless, and the data analysis from both components is user-friendly. So with every advance that we make in hyphenated technology, we get closer to the seamless combination of different analytical techniques. For this webinar, we're going to be focused on evolved gas analysis. This refers to using a secondary instrument to obtain chemical information on sample gases evolved during thermal degradation of a sample. So why is hyphenation for evolved gas analysis important? As we will discuss in more detail in a few minutes, TGA, or thermogravimetric analysis, alone yields valuable information regarding thermal stability and weight loss of a sample, but it lacks information regarding the chemistry of the evolved gases. PerkinElmer is a leader in hyphenated technology. We offer a single vendor solution. This means that everything from installation, maintenance, application support, software, and data analysis is designed with hyphenation in mind. The precise control between gases, between instruments, allows for unparalleled consistency and sensitivity. So let's talk more about evolved gas analysis. The TGA, or thermogravimetric analysis, measures the change in the mass of a sample as the sample is heated, cooled, or held at a constant temperature. As the temperature of the sample increases in an inert atmosphere such as nitrogen or helium, thermal degradation occurs and gases are evolved from the sample. So in this picture to the right, you can see the furnace design for our bottom-loading high sensitivity furnace, the TGA 8000. So the sample is actually suspended in this furnace, so very small volume, very quick heating for that furnace. So TGA is very good at answering the question of how much regarding a thermal degradation event. But TGA alone yields no information regarding the compounds or what kind of components are being decomposed. So if we take a look at this data on the screen, this is a typical TGA weight loss curve for rubber. So what we can see here is temperature on the x-axis and percent weight loss on the y-axis. And we have several weight loss events occurring due to degradation of different compounds in the rubber. So we can calculate the percent weight loss to get an idea of how much of these components are in the sample. But without further information, we do not have chemical information for these evolved components. So this requires that we probe the chemistry of the evolved gas by transferring the sample gas to a secondary instrument. So we take a look at this diagram on the right. This is a simplified diagram of a hyphenated system. So we have the TGA on the right. It's being supplied by several carrier gases to purge the balance compartment, to purge the sample compartment. And then we have the sniffer tube that sits very close to the sample, very close to the furnace. So as soon as those gases are evolved, they get moved to the transfer line. Then they get carried to a secondary instrument. So this is either FTIR, mass spec, or GC-MS. And the whole system is controlled via a pump system and a mass flow controller. So this is actually pulling gas through the system and allows us to very precisely control the flow rate and the pressure throughout the system. Okay, so let's discuss the analysis of the evolved gas in a little bit more detail. So there's several ways that we can go about analyzing the evolved gas. If we use FTIR, we probe the molecular structure based on absorption bands of different molecular bonds in the evolved gas. When measuring gas phase spectra, we can see molecular vibrations and rotations. Using mass spectrometry, we can study the ion mass fragmentation patterns of parent molecules. And with GC-MS, we add a separation step or a chromatography step in order to resolve complex mixtures of compounds. So all of these techniques can be aided by searching spectral libraries to identify unknowns. So why is it important to measure these evolved gases? So we can get several critical pieces of information regarding volatiles off-gassing at different temperatures. We can identify reactions and byproducts. We can identify materials based on simple breakdown molecules, which are subunits of the parent molecule. So all of this information gives us better understanding of complex materials and how they behave under elevated temperatures. Okay, so there are many different applications for evolved gas analysis and hyphenation. So I'll just point out a few cases. If we look at polymers, research, and quality assurance, we can study the thermal stability of polymers. This includes things like plasticizers and other additives that may be in these polymers. We can do competitive analysis or reverse engineering of different products. Hyphenation and evolved gas analysis provides an easy way to probe the chemistry of unknown samples. In general, very little sample prep is needed for this type of analysis. We take a look at academic and government research. This includes things like researching and studying new materials, as well as understanding reaction kinetics, for example, using different types of catalysts for the energy sector. We look at industrial and petrochemical applications, lubricants such as oil and grease. This is a really interesting application. These materials are often used at high temperature environments, such as in bearings and engine components. So it's important to understand the thermal stability of these components and potential thermal breakdown of additives that may be in these materials. So for environmental applications, we will discuss in a few minutes measuring soil contamination using TGIR. Microplastic research is something that we have seen a surge in recently. Using thermal degradation temperature and evolved gas analysis, we can measure the identity of unknown polymers and microplastic samples. An important application for pharmaceuticals is measuring residual solvents that may be in pharmaceutical products derived from the manufacturing process. So we want to make sure that all of these volatile compounds are not present in the final product. And there's a host of different other applications as well. Okay, let's take a closer look at the different components and instrumentation required for performing evolved gas analysis. So first, we have some type of thermal technique that heats a sample and produces the evolved gases. This is typically TGA, but STA, which stands for simultaneous simultaneous thermal analysis, is an option as well. STA gives you a TGA weight loss curve as well as a DSC signal, giving you even more data for a single run. The other benefits of STA are that temperatures of up to 1600 degrees are possible. So hyphenation is compatible with both our bottom loading high sensitivity TGA, which is the TGA8000. You can see an image of the TGA8000 here on the bottom image. And is also compatible with our robust top loading design, the TGA4000. And you can see a picture of that towards the top. So all of these thermal instruments have the capability to change environmental gas or purge gas, making combustion and oxidation studies possible. So let's focus in on the transfer line. The transfer line must be heated in order to prevent vapor phase condensation, and it must be inert in order to not cause any secondary reactions beyond the initial thermal degradation. Consistent pressure and gas flow rate must be maintained throughout the system. This is important to provide consistent data. The transfer line carries the evolved gas to the secondary instrument for chemical analysis. The secondary instrument can be FTIR, mass spec, or GCMS. If FTIR is used for the secondary instrument, which is non-destructive, we can add a third instrument, which will either be mass spec or GCMS. Okay, so this slide shows a comparison of the different hyphenation configurations that are available. So we're starting with the simplest configuration on the left and then getting more complicated as we move to the right. So the first one, TGIR. So this is coupling TGA with FTIR. This is the most common setup that we typically see. So using TGA, we get thermal degradation, weight loss events, and then the chemical information we get from FTIR, functional group analysis. The FTIR spectra essentially gives us a molecular fingerprint of the vapor phase sample. So one of the main benefits here is this is a real-time analysis. So we can continuously collect spectra throughout the entire TGA temperature ramp experiment. So as soon as those evolved gases are coming off of the sample, they're being moved or transferred to the FTIR, and we're getting a real-time data feed. We have a host of different vapor phase libraries that can help us identify different compounds. Some difficulties, in general, lower sensitivity than something like mass spec or GCMS. Also, we can run into some difficulties if we get complex mixtures of gas sample. We do have some software options that can do deconvolution and mixture searches, so we can actually identify multiple compounds in a single spectrum. But if we start getting too many compounds in the same sample, then this becomes difficult. Okay, so next let's talk about GCMS. So this is taking the evolved gas from TGA, injecting straight to the MS. So like TGIR, this is a real-time analysis throughout the whole run, so we can continuously collect mass spec data. This is generally a more sensitive technique than infrared. So if you have very small sample sizes or very dilute gas samples, this can be a good option. But again, we run into some of the same difficulties with mixtures. So complex mixtures of gases can be difficult to analyze, data can be difficult to interpret. So moving to GCMS. So here we're adding a gas chromatography step before we get to the mass spec dissection step. So this has the benefit of resolving overlapping events. So if you have complicated mixtures of gases, the chromatography step can separate those compounds and we can identify them individually. So the downside here is that we no longer have a real-time or continuous data feed. So in this case, the user would select a particular point along the TGA temperature ramp to collect a gas sample and then inject it to the GC mass spec. So the last option here we have is TGIR GC-MS. So this technique, we really get the benefits of both the continuous data feed of FTIR and also the improved sensitivity and improved resolution for complicated mixtures that we get with GC-MS. Okay, so we're going to dive down a little bit deeper into TGIR. So taking a look at the TT8000, so this is PerkinElmer's high sensitivity bottom loading TGA. So we have the balance mechanism up here at the top. A hang down wire holds a ceramic crucible where the sample would go. The furnace would be lifted up and it would surround the sample. So this furnace design is a very low volume, meaning that any evolved gases, there's not a lot of space for diluting with the purge gas. So as soon as those gases are evolved during heating, they can enter straight into the hyphenation line. So the hyphenation line is connected to the top here, and we have this sniffer tube that actually sits right above the furnace and right above the sample. So again, this allows those gases to very quickly get into the hyphenation line and go to the secondary instrument. So this helps improve sensitivity for small samples and samples with low concentrations of gases. So the sniffer tube is heated. This helps prevent condensation. It can easily be removed and cleaned. And there's a valve on the hyphenation line that you can turn on and off easily, depending on whether you want to do a traditional TGA experiment versus a hyphenation experiment. Okay, so taking a closer look at the hyphenation line. So this is what's used to connect the TGA with FTIR. There's a mass flow controller, as well as a vacuum pump that'll pull gas through the system. So the transfer line, as well as the FTIR gas cell, have the capability to be heated up to 350 degrees. So this prevents condensation of vapors in the gas line. If we take a look at the FTIR gas cell, this is called the zero gravity design. And this essentially means that the inlet and the outlet for the gas cell are offset. So this helps high molecular weight compounds or high molecular weight vapors flow through the cell without condensing either inside the cell or on this window here. If we do get condensation here, this will effectively carry over throughout the entire data collection. So it's important to prevent any kind of condensation on that window. So again, the gas cell can be heated up to 350 degrees as well. So in terms of the FTIR, the standard detector would be a DTGS. If you need increased sensitivity or increased scanning rates, then we can outfit the instrument with liquid nitrogen-cooled MCT detector. Okay, so now let's talk about some applications and look at some data. So I'll mainly be focusing on TGIR for analysis of polymers, materials, and environmental samples. Then I'll wrap up with one example showing TGGC-MS. Okay, so our first example here is looking at the thermal degradation of ethylene vinyl acetate. So EVA, this is a copolymer of ethylene and vinyl acetate. So we can see an image of the molecular structure of this polymer on the upper right-hand side. So the instrument setup we had here was the TGA 4000, and then the transfer line and the Frontier FTIR. So we have the option for fast scanning with this instrument. So we call this by separate data collection. And effectively what this does, so the interferometer is the mechanism in FTIR that varies the path length of the infrared beam. When we recombine this beam with the fixed length beam, we get an interference pattern. So this is the underlying principle of FTIR. So the interferometer starts at a center position, rotates right, rotates back to center, rotates left, and rotates back to center. So this is 4 motions. Typical data collection, we would take these 4 motions and use that to collect 1 spectra. But with this biseparate data collection, we can actually get 4 spectra for 1 revolution or 1 rotation of the interferometer. So this allows us to scan more quickly. Okay, so I want to focus in here on what types of data we get from TGIR. So if we look at this left-hand plot, this is the TGA weight loss curve. So temperature on the x-axis, percent weight loss on the y-axis. So the blue curve is our percent weight loss. So what we see here are 2 weight loss events occurring right here and right here. This red curve is the first derivative. This helps us identify where the maximum rate of weight loss is occurring. Now, if we take a look at the FTIR response, this top curve is called the Gramschmidt Plot. The Gramschmidt Plot is essentially the total or the average absorbance or infrared signal with time or with temperature. So this is continuous data collection throughout the entire TGA experiment. So we can look at this either overlaid or as split plots against the weight loss curve. So what we see is during these different weight loss events, we see a spike in this Gramschmidt plot corresponding to an increase in spectral absorbance. So at any point along this Gramschmidt plot, we can identify time or temperature, and we can extract individual FTIR spectra to get more chemical information. So what we're going to do is we're going to look at 2 points along this Gramschmidt plot that's corresponding to these 2 weight loss events. So this left-hand plot shows the first spectra from around 360 degrees Celsius. So the spectra we searched against a spectral database, and we identified as acetic acid. So this acetic acid is coming from the breakdown of the vinyl acetate polymer. Now, if we take a second spectra snapshot, closer to 500 degrees, we see absorption peaks related to carbon-carbon, carbon-hydrogen stretch from aliphatic hydrocarbons derived from the breakdown of the polymer hydrocarbon backbone. So what kind of information did we get from this analysis? So TGA shows us degradation temperatures. TGA shows us percent weight loss. So these help answer questions regarding material properties, thermal stability, and answers the question, how much of these different components are in our sample. And then we can use the FTIR spectra to get chemical information, chemical identification, and we're aided by the ability to easily search large spectral databases. Okay, so our next example here is looking for plasticizers in polymer mixtures. So plasticizers are chemicals that are commonly added to polymers to change their physical properties. So this includes things like changing glass transition temperature, or the temperature where the material transitions between being rigid and hard to soft and pliable. It can affect material hardness, strength, processability, flexibility. So some of the issues is these plasticizers can evaporate upon heating or can dissipate upon aging. So if you ever get inside of a new car and you smell that nice new car smell, that's actually plasticizers from all the plastics and fabrics inside the car being off-gassed. So some of these plasticizers can pose a health risk. So understanding thermal properties and the off-gassing behavior of these plasticizers is important. So for this experiment, we have 2 samples. We have paint with plasticizer and then a paint sample without plasticizer. So we've used the TGA 8000, the TL8000 transfer line, and then the Frontier FTIR. So if we look at the TGA weight loss curve, so we have two curves here. The red curve is the sample without plasticizer. The blue curve is the sample with plasticizer. So we see different weight loss events occurring. We see 3 weight loss events in the sample without plasticizer and 4 with the plasticizer. So we have this weight loss event here that's specific to the sample with plasticizer. So we can identify this as the weight loss or the degradation or the off-gassing of the actual plasticizer. So if we focus in on just the sample with the plasticizer, we can measure simple delta Y calculation, and see our plasticizer concentration is about 8.5% of the total sample weight. If we look at our FTIR response, so this is the Gramschmidt plot, we can see during this individual weight loss event of the plasticizer, we can pull out the FTIR spectrum. Then we can take the spectrum, search it against the spectral library, and we actually get a positive identification for the chemical identity of the plasticizer. So we get citric acid, tributyl ester acetate. So using TGIR, we were able to determine the amounts of plasticizer in the sample, as well as the chemical identity of the plasticizer, and what temperature it's evolving from the sample. Okay, so the next example here is investigating soil pollution with TGIR. So a little bit of background. It's common for soil around fuel tanks in the ground, whether it's a gas, at a gas station or maybe home heating oil in a residential area. If these tanks leak, then we can get fuel contamination on the soil. This can cause problems with groundwater, runoff. So the typical method of identifying this would be to collect a soil sample, do an extraction on the soil, and then either measure these extracts with FTIR or with GCMS. So this extraction step, is an extra step in the process that can be time-consuming and costly. So what we would like to do is show that TGIR can be offered as a solution to minimize sample prep and minimize analysis time to identify soil either contaminated or not contaminated with fuel. So for the sample, we have a soil sample mixed with diesel fuel. The TGA temperature ramp is from 30 to 800 degrees at 20 degrees per minute. And then we're holding the transfer line at 280 degrees Celsius and collecting FTIR spectra every 12 seconds. Okay, so if we look at the TGA weight loss curve, we can see we have 3 main areas of weight loss. So between 30 and 100 degrees, between 100 and 250 degrees, and then between 250 and 600 degrees. Okay, so this plot shows our weight loss curve in red, overlaid with the Gramschmidt plot. So this is the spectral response. So we can see peaks in the average intensity of the FTIR spectra as we're going through these different weight loss events. So we're going to take a few snapshots over time at specific temperatures, and then look at the FTIR spectra. So on this plot, we have the Gramschmidt plot. So this is the average spectral intensity through time or through temperature. And we can also plot specific absorption bands or bands corresponding to specific functional groups. So the green curve is a carbon-hydrogen stretch corresponding to alkane, hydrocarbon. And then the blue curve is a carbon-hydrogen stretch corresponding to alkene, hydrocarbon backbone, that's specific to unsaturated carbon bonds in biodiesel. So these dotted lines represent the point at which we're taking a spectra snapshot that are plotted over on the right-hand side. So the first snapshot we see here is from 230 degrees. And the FTIR spectra shows us mainly carbon-hydrogen stretching from this alkane characteristic of diesel. So if we look at the second snapshot at 240 degrees, so evolving, at higher concentrations, just at a slightly higher temperature, we see some other spectral features appear. So we have this shoulder at 315 wave number. This is corresponding to alkene carbon-hydrogen stretching. And then we also have this peak at 1745 wave number. So this is corresponding to the ester bond in fatty acid methyl esters from biodiesel. So if we look at this higher temperature spectra from 430 degrees, we're mainly seeing carbon dioxide. This is mainly from combustion of organic matter in the soil. So what this analysis has showed us is that our soil is indeed contaminated with diesel fuel. And then we get even more information based on looking at the spectra through time. We can see that we have biodiesel in this contamination as well. Okay, so the last example that I'll talk about is a TGGCMS experiment. So here we have the benefit of using gas chromatography to separate complex mixtures in the gas sample. So here we looked at Thermoset Polymers used for 3D printing. So 3D printers routinely use thermoplastic polymers for printing. However, advanced materials can be printed using thermoset precursors. So the difference between thermoplastic and a thermoset is a thermoplastic can be heated, melted, extruded, or molded into a shape. It can be reheated, remelted, and then reprocessed. Where a thermoset polymer undergoes a curing or cross-linking or polymerization reaction that typically uses some type of initiator. So after this curing has happened, the material becomes very strong and is fixed. So upon further heating, you don't get melting and reprocessing, you just get thermal degradation. So the goal of this experiment is to identify this initiator compound in thermoset precursor and see what is the temperature in which this evolves and get some information about the chemical identity of this precursor, or excuse me, of this initiator. Okay, so if we take a look at the TGA weight loss curve, we see a very minor weight loss event here, accounting for about 0.2% of the weight loss. And then we have a major weight loss event occurring here at 600 degrees. So what appears to be happening is we have some slight off-gassing of the sample at 300 degrees, and then we have the primary polymer degradation occurring at 600 degrees. So using TGGCMS, we can collect a gas aliquot, or gas sample, at 315 degrees, inject in the GCMS. So the upper plot shows the chromatogram. So we see several different compounds being eluted here. And then we can use the mass spec to investigate the ion fragmentation pattern to get chemical information about these compounds. So what we're seeing here is a linear hydrocarbon with carbon triple bonded to nitrogen. So this is a nitrile compound. So initiators are commonly nitrile compounds and can possibly be used to initiate the polymerization reaction in the thermoset polymer. So now we can take another snapshot at 600 degrees. We can look at the chromatogram, and then we can get identification using the mass spectra, and then we can do spectra searches using the NIST database. So what we're seeing here are phenols, biphenyls, and other aromatic compounds. These compounds are characteristic of aramid group polymers. This is things like Kevlar or Nomex. So these are characteristic aromatic structures of that kind of polymer as it's undergoing thermal degradation. So in summary, we were able to use the TGA to show at what temperature these volatiles evolve and how much are evolving. And then we could use the GCMS to take this complex mixture of gases and elute the compounds and then measure them with the mass spec. Okay, so in summary, in conclusion, we've talked about hyphenated technology, we've talked about evolved gas analysis. Different spectroscopies can be easily interfaced to thermal analysis. We can get significant information from both of these techniques. So this TGA and then the secondary instrument. So the point is extracting more information from a single sample or a single analysis. So TGA can answer the question of how much or what temperature compounds are degraded. And then the secondary technique can be used to get additional chemical information about the sample. So today we focus mainly on TGIR, but stay tuned. We'll be offering more webinars focused on TG mass spec and then TG GCMS as well. So I'd like to thank everyone for their attention, and I will open up the floor for questions.
Excellent. Thanks, Warren. At this point, we are live for any questions that you all might have. We did have a few questions that we wanted to just present up front, Warren. What is the typical sample size for TGA?
Yeah, that's a good question. So the typical sample size for TGA is going to be around 10 milligrams. So depending on how large your weight loss event is and how concentrated those evolved gases are, particularly for interfacing with hyphenation for TGIR, you may want to increase the sample size. So if you're not getting a very good FTIR signal, you can easily increase the sample size. This will increase the amount of evolved gases getting sent to the FTIR. On the other hand, if you see that your FTIR spectra is getting saturated, maybe your absorption peaks are topping out, you can decrease the sample size, maybe try something like 2 to 5 milligrams.
Gotcha. Thanks, Warren. Another question is, what about the resolution for IR spectra? What is acceptable and how can we improve it?
Yeah, so spectral resolution. General guidelines, if you're just doing a benchtop FTIR measurement of a solid sample, 8 wave number resolution typically will give you all the information you need to see. So when you're dealing with vapor phase spectra, we get molecular vibrations and we also see molecular rotations. So these rotation vibrations are actually much more narrow in the peak. So in order to see these rotational spectra, we need to increase the spectral resolution. So something like 1 or 2 wave number resolution. That being said, identifying compounds, it's not always necessary to see this rotational spectra. You'll still get vibrational spectra even if you maintain a resolution of something like 4 or 8 wave number resolution. The frontier FTIR can go well below half a wave number resolution, so you can definitely see those vapor phase rotations if you need to. But there is some trade-off between scan speed, signal to noise ratio, and spectral resolution. So typically, as you have a higher resolution, the scan slows down and you may get more noise.
Okay. Had another user question. Does a liquid sample need to be particle-free?
No, you can put slurries or turbid samples in the TGA. That should not be any problem. What will happen likely with your analysis is you may see several weight loss events corresponding to, whatever your liquid is. And you may see another response corresponding to whatever the solid is.
Excellent. Let's see. Here's another one. What temperature scan rate do you recommend for TGA IR?
So the scan rates, a typical scan rate for TGA will be between 10 and 20 degrees per minute. So this is a good starting point for any type of sample. If you see that your evolved gas is maybe very low concentration and you're not getting a very good signal, then you can try to increase the scan rate. If we get these compounds evolving at a faster rate, this is effectively a larger concentration or a larger slug of evolved gas that can be moved to, the FTIR or to a different instrument at a higher concentration. On the other hand, if you have thermal weight loss events that are co-eluting, so they're overlapping, you can try to slow down the scan to try to get better resolution of these different weight loss events and different compounds that correspond to those events. But there is some trade-off. If you slow down the scan too much, the slower you go, the lower concentration your gas phase sample will be.
Gotcha. Thanks, Warren. This one I'll ask in tandem because they're actually sort of similar, one and the same. Can you comment on cleaning the transfer line and how often it needs to be cleaned? And I guess in tandem with that, the TGA design, is there any chance of residue buildup on the TGA, and how do you clean it?
Okay, yeah, that's a great question. So in terms of the transfer line, there's an easy way you can check the cleanliness of it after your analysis. So if you just collect some spectra of the gas cell after your analysis is done, before you take a new reference or a new background spectra, it's possible to see any kind of accumulated or condensed sample on the window. And if this is the case, then it may require that you clean the windows in the gas cell, or they're actually easily replaceable as well. But if you don't see any residue, then you can assume that your system is clean, and then you're good to make another run. In terms of the hyphenation interface with the TGA, so we call this the sniffer tube that sits very close to the furnace. So that's actually easy to remove. You can clean it with solvents, remove any kind of condensed material on this. And then in terms of cleanliness for the TGA, the furnace area is covered with a quartz liner. So you can take this quartz liner out, you can clean it, you can put it in a furnace, raise it to a high temperature, bake off any compounds that are on the liner. So, the rate in cleaning depends very much on the type of sample. If you have something that's very volatile, something that's low molecular weight, you may not have a lot of need for cleaning and maintenance. Whereas if you have some kind of very dirty samples, then obviously cleaning is going to be more of a routine.
Gotcha. Let's see. I think we have one more question here. What percentage of the gas generated by TGA gets transferred to the sniffer tube?
Yeah, that's a good question. So in general, the TGA has a purge port going to the balance mechanism, and then a purge going to the sample area or the furnace. So that effectively creates a positive pressure in the TGA sample area. So this keeps out any kind of environmental atmospheric gases from getting, in the hyphenation line and into your sample. So on the back end of the hyphenated system, we have a pump and a mass flow controller that will pull gas through the system. So it's important to keep that flow rate for the purge in the TGA slightly higher than the flow rate being pulled from the back end through that the pump in the hyphenation system. So ideally you want about 5 to 10% of your gas being vented out of the TGA, and then about 90% of that gas is going to go through the hyphenation system.
Awesome. All right. Thanks, Warren. Hey, well, I appreciate your talk today, Warren. It was great. And you spoke about what hyphenated techniques are, the different types of techniques, and the application examples of the different techniques. And you can see the power and the combination of these techniques and how they can give you much more information. So, what I'll throw out there to close is, if you all have any questions whatsoever, please reach out to PerkinElmer at PerkinElmer.com, or you can come to our website. And if you know your local representative, please reach out to your local representative for more questions, or myself or Warren, and we'd be happy to answer those and get you situated.